highlighting here. So where x and y are both positive. So that's why I'm integrating between 0 and something. So now the, the plane has equation z equal to 1 minus x minus y. And I think that here I am writing this plane as a function of x instead. So I have that x is equal to 1 minus z minus y. So x will be between uh, x will be between 0 and 1 minus z minus y, right? Now you have to figure out which are the, I mean, you can, one of the three will be, let's say, the free variable. So z will be between 0 and 1, because so I decided. Because if you take that plane and you intersect with the z plane, you get that the maximum value that z can reach is 1. So z is between 0 and 1. And the leftover is y. So now you have to see that, let me go back to the picture. Okay, so you have to see that, look at this side here. Y will be between 0, so here, and this straight line essentially, and this straight line in the z y plane as equation 1 minus z, right? So this will be the endpoint for y. It's essentially the projection on the yeah, I mean, the green triangle is the projection of the whole pyramid on the zy plane, right? So the green triangle is the projection of the whole pyramid on the zy plane. So that's the one that we're interested in. So the two-dimensional domain. Is it any clearer?
Yeah, it makes sense. But the reason why we did this is because if you do it in the normal bounds, then the integral just becomes harder.
Yeah, exactly. I think it gets quite tricky to. I'm not sure actually. Let's see. If you integrate, yeah, you have a power of 3, and then you have to integrate in y. I mean, you might be able to do that anyway. I didn't do the computation. I just thought that this was easier to integrate, but you might try in the original setting. So essentially, I mean, you see that there is a lot of symmetries here going on. So the role that was played by Z in the beginning is played now by X. So this is the logic behind when you do this switching, when you switch this integration order. I think let's see. So if you integrate in z first, you get z to the power of 3, and then you get a polynomial uh, to the power of 3, and then you have to integrate in y, and you get, yeah, I think it should be double in also in the original. There are no square roots or anything strange. Sometimes you're not actually able to perform an integration in some specific order, but you are able to perform an integration if you change the integration order. This doesn't seem the case though, so maybe you can try yourself. I'll leave this here. So try, not in green though. Try if you can perform the integration using the original order. Sometimes changing the integration order. Helps a lot with the computations. So try to see if this is the case or if there is not a huge improvement integration. Yeah, some words here. Okay. Let's see the number 9. Number 9 is integral over triple integral over r of sine of pi of this. Sometimes I might write just one integral sign, while I mean that I'm integrating over a three-dimensional domain. This is used very often in well, this is actually the standard notation for multiple integrals, actually. The reason is, of course, compactness. I mean, if you had to integrate over R30, then you had to do 30 different, this doesn't make sense. So you just draw one. So it is clear from the context what's what is the dimension of the space, and specifically the domain in our case R is what? Let's see, the pyramid. So pyramid with vertices origin 0, 0, 0, 0, 1, 0, 1, 1, 0, 1, 1, 1, and 0, 1, 1. So let's see. So this pyramid is this, so one vertex is here. So then we have 0, 1, 0, so we are here. We have 1, 1, 0, so we are here. And then we have 0 in x, and this, so we are here, and then we are here. So we have this pyramid, right? As usual, my picture sucks, but yeah, maybe I should have left like this. And these are okay. So let's see this integration. We have to figure out the endpoints of this this object here, and it seems that so we can. So for instance, I mean, I guess that in this case, the order of integration is very important, because if you start integrating in y, well, maybe not, maybe you can get out of that. Yeah, you have something, you generate a singularity actually in some sense, because you get the cosine of pi of y to the power of 3 and then divided by something, y to the power of 2, because you have to compensate to the chain rule. So I think that a good idea here is to leave the y as a last variable, Well, let's see at least. So to me, it looks like that y is between 0 and 1 if we leave y as a last variable to integrate. So what about x and z? Okay, so I guess that let's see. I cannot really see very well from this picture. Maybe I mean yeah. I guess that yeah. I guess that x will be between 0 and y because I'm considering this line, red line here, and the projection of the pyramid on the xy plane is this triangle. And this is described by what I've written there. Which is not very clear from my picture though, and about Z, I think that it's the same thing. I think Z is between 0 and Y also. For the same reason you pick this, and you have this triangle here. And then all together should generate this pyramid, I think. So these are the endpoints. Let me give a look to it one more time. Yeah, I think this is correct. Yes, so this is R. And then we can write the integral I. That's a triple integral. We said that we leave y as the last. And then we have this integral of sine pi y to the power of 3 in dx dz dy. So this is equal to integral between 0 and 1, integral between 0 and y. I have a y here now, sine of whatever, in dz dy. Now I have to go to the other page. Now you see, you integrate again, you get the integral between 0 and 1, you get the y squared, sine of pi y to the 3 in dy. And now we can integrate straightforwardly this object here, because that's exactly the derivative of minus cosine y this divided by pi, 3 pi between 1 and 0, and this is equal to 2 divided by 3 pi. So you see that in this case the integration order led us to a very easy calculation. I'm not sure about the other orders. So if you get stuck into calculations, that's not, maybe it's not you, it's just that it's not really possible to go ahead in that direction. You have to try to change the integration order. Yes. All right. Okay. Do you have any question? I can state the number 11 and then we can have a break. So we want to compute the integral I, which is a triple integral over R of 1 divided by x plus y plus z to the power of 3 in dv, where R is the region bounded by the 6 planes z equal to 1, z equal to 0, z equal to, no, z equal to 2, y equal to 0, y equal to z, x equal to 0, x equal to y plus z. And yeah, okay, let's take a break for 15 minutes. We'll start again in 15 minutes. If you have questions, you can just type them. I'm gonna get a coffee and then be right back. Okay, guys, we are back. So I am back. How about you? Yep. So we were looking at exercise 11, right? So we were supposed to compute a bunch of planes um, who determines some sort of polytope, I think. And we want to compute this triple integral. The task is always the same. I hope that there are only computation for today. Okay, well, let's do these computations. Well, the endpoints here are already written essentially because it's pretty clear what's going on. So the integral I is equal to the triple integral between 1 and 2, between 0 and z, and between 0 and y plus z of 1 divided by x plus y plus z to the power of 3 in dx, dy, dz. Okay, so we integrate in x first. We get this is equal to minus 1/2 times x plus y plus z between y plus z 0 in dy dz, right? And this is equal to minus 1/2 integral and we do get okay, so this should be 2 to the minus 2 minus 1 y plus z to the minus 2 in dy dz. And if you write and that's 3 divided by 8, and then we have the same integral 1 divided by, I just rewrote the expression, and now we perform the integration in y, and we get that this is equal to 3 divided by 8 integral between 1 and 2 y plus z to the power of 1, or actually minus 1, this in the z, and this is equal to 3 divided by 8 1 this in dz, which is equal to 3 divided by 16 times logarithm of z between 2 and 1. And this is equal to 3 logarithm this divided by 16. So this is number 11. Let me just check one thing. Okay, no questions. Let's see the number 12 then. You want to compute I, where I is the integral over R of cos x cos y cos z in dv, with R is the set x positive, y positive, z positive, and everything below pi, the sum of the coordinates below pi. So we have again a pi pyramid, a portion of a pyramid or a pyramid. So we have something like this, like before. We will have something like this. So this guy will be the plane x. Wait. X plus y plus z equal to pi, and then we are in the positive octant. And this is x, and this is y, and this is z. Yeah. Let me fix this. Okay, so what is this? So this is I will be the integral between 0 and pi of the integral between 0 and pi minus z, and the integral between 0 and pi minus y minus z of the function dx dy dz. So what is this? We integrate in x first. And we do get cosine of y, cosine of z, and then we have sine of pi minus y minus z. Then I use periodicity of sine. I get this is equal to sine of y plus z in dy dz, right? Okay, so now this gets a bit complicated. Okay, so to get rid of this, I have to use this Werner formulas, because I have a product that I want to turn into a sum. Let's see if these Werner formulas are written somewhere in the book or no. No, they're just integral tables. Yeah, I just want to give you a reference. I have the formula written down, but no, this is polynomials, functions, trigonometric functions, addition. Oh, good. There are no formulas on this book, maybe. Well, let's see, there is somebody writing. No, I mean, I want to write this. So I have a product between cosine of y and sine of y plus z. I want to write this object as a sum of something, right? So now, so I claim, and this is actually true. So cosine of y times sine of y plus z is equal to 1/2 times sine of z plus sine of 2 times y plus z. And this is because the Werner formulas. So let's see if I can show you the Wikipedia page. No, this is for Binitonelli, Werner. Prostaphrasis. Yes, so I have, I mean, can you see, yes, can you see the page? I am using of this, you see a bunch of formulas here in this page. So we had cosine of y times the sine of y plus z. So we have cosine times sine. So I'm using the fourth one. And then you see that I have a problem with the sign, maybe. Because I put a plus, but here there is a minus. Sine of, yes, minus y gives me z, and that's correct, but it should be a minus in front. Yes, so yeah, I guess there is a minus here. I guess there should be a minus. No, not here, but in front of this. Okay, looks like correct now. Well, according to these formulas by Prost Afäresis or Werner formulas, we have that this integral is equal to 1/2, and then we have integral between 0 and pi, and then we keep the cosine of z, and then we integrate that other thing, and I get minus minus cosine 2y plus z divided by 2, and then I'm integrating in y. Looks like there is a minus here. Y sine of z between pi minus z and 0 in dz. Okay. So this is going to be equal to 1/2 integral of this cosine of z times, let's see, so I get minus cosine. Okay, so we have 2x, sorry, 2y, we have 2 pi minus 2z plus z, so I guess that this is 2 pi minus z divided by 2, and then I have minus pi minus z sine z plus cosine z divided by 2 and 0. So that's the only thing that's left. Yes. So now I get this is equal to 1/2. And then I add a cosine of z in front. So I get integral between 0 and what? And pi of minus cosine z times cosine of 2 pi minus z, which is equal to cosine of z because of periodicity. So this guy is equal to cosine of z. And then we have plus cosine squared z divided by 2. So these two, they cancel. And then I have minus, let's see, minus or plus, minus pi minus z sine of z, and then everything is in dz. So the conclusion is that this is equal to z minus pi times sine of z in dz, and then you do integration by parts. There was a 2 maybe also, let's see. Ah, no, 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 wait. Because I written. Yeah. Pi. There was sine, cosine in dz. So here we have actually sine of 2z dz divided by 2. I can actually write immediately divided by 4 here. And this should be, if you integrate by parts, you should be able to get. So pi divided by 8. I'm not sure about the sign, if it is a plus or minus, but you can check for yourself. This is more or less how this integral is supposed to be solved. So yeah, we use these Werner formulas. Actually, this would be, I mean, I think this formula in a possible exam would be given in the exam itself. So something like you have this integral, but then you have also this formula and try to find out a way to use it properly. So yeah, questions? No questions. Okay, I go ahead. We have two problems left. So 14 and 27. Number 14, we want to find the volume of the region lying inside the cylinder, x squared plus y squared times 4 equal to 4 above the xy plane and below the plane z equal to 2 plus x. The Wikipedia page was I just googled Werner formulas, and you have to click on prostapheresis, so you can find them. Werner and prostapheresis are essentially the inverse of each other. I mean, in the end, the formula that I wrote before, if you go back, the formula was something like cosine of A times the sine of B is equal to sine of A plus B minus sine of A minus B divided by 2. You can just deduce this formula by just using the addition formulas for sines, which is something that you should know. I think you expand the sine of A plus B and sine of A minus B and you get the product somehow. So shouldn't be too hard to prove them. No worries. Okay. So what is this now? This is some cylinder. This is some cylinder. I mean, the cross sections are now elliptical. They are ellipses. So let me. So at y equal to 0, we have that this is plus minus 2, and for x equal to 0, we get 1. So it's something like this. So we have some cylinder, and then we have some plane that I don't know. So we want to, to compute the volume of what is below this plane, above the plane xy, and inside the cylinder, right? Yes. So the volume that we want to compute is going to be equal to triple integral. We have that z will be between 0 and 2 plus x. And then we can write that x is between 2 times the square root of 1 minus y squared and minus 2 times 1 minus y squared. And then we have that that y is between minus 1 and 1, right? And the function to be integrated is just dx dy. So dz is the first, dx is the second, and the y is the third. So this is equal to the integral between minus 1 and 1, integral between minus 2 square root of whatever, this, and then we have 2 plus x dx dy as a last. Yes. Okay, so what is this equal to? So now again we have to integrate the function x on a symmetric domain, so the second part is actually equal to 0. So this is equal to 2 times, it's essentially 2 times the ellipse less or equal than 4 in the A, if you want to, plus the same thing but with x here, less or equal than 4 in the A, and now this is equal to 0 by symmetries. Change of variables and so on. Now the first one is just 2 times the area of the ellipse that we know that is pi times a times b. So if the ellipse is written for an ellipse of equation x squared divided by a squared plus y squared divided by b squared equal to 1, area of ellipse is equal to pi times a times b. Of course, this you can prove by double integrals, but I don't want to do the calculations again. So in our case, you have that b is equal to 1, a is equal to 2. So in our case, this is equal to pi times 2 times 2. So it's equal to 4 pi. And that's the integral. Okay. Right, so we want to compute now the last integral. This is equal to integral between 0 and 1 in the z, integral between z and 1 in the x, integral between 0 and x e to the this in dy. Yes, so this exercise is flagged as hard because the problem is that I guess that if you try to integrate in the order in which it is written, it's very hard to. I mean, you cannot integrate it. First of all, we have to find out. We have to try to understand what's the shape of the domain here. It's written. So the domain of integration is z less or equal than 1 greater or equal than 0, x between 1 and z, and z, and y is less or equal than x and greater or equal than 0. So if you try to make a picture of this thing, um, this is x, this is y, and this is z. It looks like let's see. Z is between 0 and 1, so this is and and y is between 0 and x, right? So we have something like this. Between 0 and x. But okay, let me start with the x. X is between z and 1. So I guess that I have something like this. So x is between z and 1. So we have this triangle here. And y is between 0 and x. So I guess we have between 0 and x, we have this triangle here. So we have some sort of pyramid here. Yes, this is the pyramid that we have. So now the problem is, so problem, no, issue. Okay, well let's try to integrate it. It might be interesting to see why we get stuck. So we try to solve I as written. So we don't modify the order of integration. Okay, let's see. So we had integral between 0 and 1 in dz, integral between 0 and x, no, between z and 1 dx, and then we integrate in y. So we do get y this, no, to the power of 3 between x and 0, which is equal to z and y, and this is just x e to the power of x to the power of 3 in dx, right? And now I simply think that we cannot integrate any further because this is not the derivative of anything. We have to switch the integration order. We have to put the x as a last variable in which we do integrate. So this doesn't work. We cannot integrate any further. So let's then try to switch the integration order. So idea, leave x as last variable. So we need to rewrite the domain that we had. So if we write, did it have a name? No. So domain of integration is equal to so x between 0 and 1, and now we have to see the other variables. I guess that if the picture is the one that I wrote, also z will be between 0 and x, and y will be between 0 and x. So y is between 0 and x, and it remains the same, but z is between 0 and x2. Now the x is the independent variable, right? Doesn't depend on anything. Now our integral rewrites as integral between 0 and 1 dx, uh, integral between 0 and x dy, and integral between 0 and x in dz of the function e to the whatever in z and in y. So I get integral between 1 and 0 of x squared e to the x to the power of 3 in dx, and now this can be easily integrated. So this is now equal to this divided by 3 between 1 and 0. So this is equal to e minus 1 divided by 3. So this is another example that shows the importance of integration order. So there might be shortcuts to, or actually there might be problems if you try one order. You might get stuck like we got stuck in the previous case here. So some red flag. And this means that you have to change integration order, and then you have to rewrite the domain accordingly. Yes. So this was the last problem for today. In principle, we have still like 13 minutes left. If you don't have questions, you're free to go. If you have questions, I'll stay here for a few more minutes, or if you have some request or something. I'm gonna post this exercises problem, sheet of problems on the Canvas page. Try to give it a look. As I said, it's not mandatory or anything. It's just somebody asked me for some curious problems or more, advanced stuff. So I thought about that, and I found some cool stuff. So you can give it a look. The number 1 is going to be quite hard. The number 2 and number 3 should be doable, but they are very instructive, I think. They teach you something. So yeah, if you have like a couple of hours free time, just try to think about those problems if you want. Yeah. Okay. Can you show in the picture how you got to the new boundaries of integration for the last problem? Yes. The picture was this one, right? So you see that if x is between 0 and 1, we are inside this this pyramid. So it means that y has to be between 0 and x, because you consider this straight line. This straight line is y equal to x, and we are inside. And the same thing happens for z. This straight line here is z equal to x in the xz plane, and we are inside. We are inside in this sense. So we go from 0 to x. So both y and z are between 0 and x, while x is free. Yes, no worries. Yeah, that's probably the hardest part in triple double integration to get to the correct domain and rewrite the integration order. Yeah, to rewrite the domain when you change the integration order. But yeah, you have to do a bunch of problems and get used to this. Other questions? Yeah, that's a good question. Well, there is not an answer, of course. You have to play with inequalities in general. I mean, if you have like a domain which is given by a bunch of inequalities, you have to reshuffle them around and see if you manage to. Um, I think, I mean, rewriting the domain and also rewriting the domain when you change the variables, for instance, so that's rather complicated. You have to be careful. When a picture is not available, you have to play with the inequalities. We haven't seen examples. I'm not sure that we will see examples of that, but I mean, you have to come up with a new set of inequalities, and to do that, you have to play with the original inequalities. So, for example, you have that x is less or equal than blah blah, and something you play with them, and then you try to reverse them. So that's more or less what you are supposed to do, but it's not always easy. So there is some, there is not a rule. I mean, of course, you have to do a lot of exercises and try to get used to this. But there are not even examples in the book. I mean, you can cook up very hard problems in integration, in which the difficulty is merely rewriting the domain of integration according to a change of variable or a new integration order. So, but this book doesn't have, I think, complicated things. Mm. Well, okay. If there are no any other question, I think we can close the seminar here. yeah. Okay, so if there are no other questions, I will close the seminar and yeah, have a nice weekend, and I'll see you with the very last seminars, I think the next week. I think we will do the last problems from the book, and then likely some old exam. Yeah. Okay. Have a nice weekend.